In 1903, I became the first woman to win the Nobel Prize in physics, and I won it for proving that atoms can destroy themselves. The scientific establishment had spent centuries insisting that atoms were indestructible and eternal, the final indivisible building blocks of all reality, from Dalton to Mendeleev to every chemist since the ancient Greek Democritus first proposed the atom. I showed them evidence that atoms spontaneously tear themselves apart, transform into entirely different elements, and release energy that seemed to violate the fundamental laws of thermodynamics. They faced a choice between accepting that my measurements were wrong or accepting that everything they believed about matter was incomplete. My measurements were not wrong. What I discovered in a leaking shed in Paris would eventually split into two paths, one leading to radiation therapy that today saves millions of cancer patients, and the other to the atomic bombs that fell on Hiroshima and Nagasaki. The smoke detector in your ceiling exists because of this work, and so do the Voyager probes still transmitting from beyond our solar system, and so does the carbon dating that reveals the age of ancient bones. All of these exist because atoms are not what we once believed them to be. The atom, that supposed foundation of permanence, contains within itself the seeds of its own transformation. This is the story of how we discovered it. Not what we believed, but what we observed. And the observations shattered a fundamental assumption that had stood for over 2,000 years. The year was 1896, 1 year after Wilhelm Röntgen had stunned the world with his discovery of X-rays, invisible rays that could pass through flesh and photograph bones. The scientific community was electrified, and everyone was hunting for new rays, new invisible phenomena. A colleague named Henri Becquerel was investigating whether phosphorescent materials, substances that glow after absorbing light, might emit something similar to X-rays. Becquerel was working with uranium salts, and one cloudy February day, unable to conduct his planned experiment due to lack of sunlight, he placed his uranium sample in a drawer, resting on a photographic plate wrapped in thick black paper. He intended to wait for better weather. Days later, when he developed that plate expecting nothing, he found it darkened and fogged, as if intense light had touched it. No light could have penetrated the black paper, and the uranium had been sitting in complete darkness. Something was emerging from that uranium, something invisible that could penetrate opaque materials and affect photographic emulsions, something that required no external energy source whatsoever. And here is what separated this from everything that came before. The uranium emitted this something constantly, continuously, spontaneously, regardless of whether it was exposed to light or kept in darkness, regardless of whether it was heated or cooled, regardless of whether it existed as a crystal or dissolved in acid. The emission arose from the uranium itself, asking nothing from its environment. When I learned of this phenomenon, I recognized immediately that it demanded systematic investigation. Not speculation, not theory, but measurement. Precise and repeatable and quantifiable. This became the subject of my doctoral research, though many considered it an obscure curiosity, and Becquerel himself had largely moved on to other problems. I was drawn to the mystery itself because here was a phenomenon that defied explanation, and no one had yet investigated its fundamental nature with sufficient rigor. My husband Pierre had designed, together with his brother Jacques, an extraordinarily sensitive instrument called a piezoelectric electrometer. They had discovered that certain crystals, when compressed, generate electrical voltage, and this piezoelectric effect allowed them to build a device capable of detecting the faintest electrical currents imaginable. This became my primary tool, far more precise than Becquerel's photographic methods. When these invisible rays pass through air, they ionize it by stripping electrons from air molecules, creating charged particles that can conduct electricity. This ionization can be measured with exquisite precision. Rather than relying on the subjective darkness of a photographic impression, I measured the electrical effect directly, and this gave me numbers, comparable data, science that could be replicated and verified. My first task was confirming Becquerel's observations. Uranium compounds emitted rays regardless of their physical state, whether solid or powdered, crystalline or amorphous, pure or mixed in compounds, wet or dry. The emission held constant, unchanging, and here is the observation that would lead to everything else. The strength of the emission depended only on the quantity of uranium present in the sample, and nothing else mattered. Stop and consider what that implies. The chemical compound was irrelevant, and the molecular arrangement was irrelevant. Whether the uranium was bonded to oxygen or chlorine, or existed in pure metallic form made no difference whatsoever. The emission came from the uranium atoms themselves, independent of their chemical context. This was not a molecular phenomenon, and it was not a chemical reaction in any ordinary sense. I concluded, And this was perhaps my most fundamental contribution to science, that this radiation was an atomic property of uranium. The atom itself was doing something, emitting something from within. The mathematics of this emission, I would later learn, follows the same exponential curve that governs compound interest, population growth, and the spread of epidemics. Nature uses this pattern everywhere, in your retirement account and in the heart of decaying atoms, and the same equation appears in both, but I am getting ahead of the story. I tested every element I could obtain, dozens of substances in pure form and in compounds, and I found that thorium also possessed this property of spontaneous emission. I called this property radioactivity, a term I coined that is now used in every language. And that's when I examined minerals, natural ores from the earth, and here I encountered something that should have been impossible. Pitchblende, a uranium ore from the mines of Joachimsthal in Bohemia, registered far more activity than the quantity of uranium it contained could possibly explain. The same anomaly appeared in chalcolite, with radioactivity 4 times stronger than pure uranium could account for. If radioactivity was proportional to uranium content, and if I had measured uranium content precisely, which I had, then these minerals were emitting more radiation than their uranium alone could produce. Only one logical explanation existed. These minerals contained something else, another substance, an element entirely unknown to chemistry, an element far more radioactive than uranium itself, present in quantities so minute that no chemist had ever detected it. Pierre abandoned his own research on crystals and magnetism, research he had pursued for years and that had already yielded discoveries important enough to earn him a doctoral degree, and joined me in the search. The work consumed us both. We were given a space to work, a converted shed that had formerly served as a dissection room for the medical school, with no waterproofing and no heat. Winter temperatures inside sometimes fell to 6 degrees Celsius. A visiting German chemist, Wilhelm Ostwald, later described it as something between a stable and a potato cellar. Today, the particle physics laboratory at CERN costs over $13 billion, and our discoveries were made with equipment worth less than our bicycles. That shed was ours, and we did not complain, because we were hunting something that had never been found, hunting it with an electrometer, intuition, and the willingness to process literally tons of raw material in search of invisible traces. The shed became our world. We worked there from morning until night, sometimes continuing by the glow of gas lamps, and the chemical separations required constant attention. I stirred enormous vats of boiling solutions with iron rods nearly as tall as I was, transferring precipitates, monitoring crystallizations, measuring radioactivity at every step. This was physical labor as much as intellectual work, and my hands grew chapped and scarred from the corrosive chemicals, while the fumes made our eyes water and our throats burn. But when a separation was complete, when a fraction showed heightened radioactivity, when the electrometer needle swung further than it had before, there was a satisfaction unlike any other, because we were on the trail of something real. The work was chemical separation on an enormous scale. We obtained tons of pitchblende residue, material the mines discarded as worthless after extracting the uranium, and we begged it from the Austrian government, paying only for transportation. And that's when the painstaking process began. Dissolving, precipitating, crystallizing, measuring, keeping only the most active portions, discarding the rest, and repeating. Thousands of crystallizations followed, each one concentrating the unknown element further. July of 1898 brought our announcement of the probable existence of an element we named polonium, after my homeland, Poland, which at that time did not exist on any map because it had been partitioned among Russia, Prussia, and Austria. December of that year brought another announcement, radium, from the Latin word for ray. But announcement is not proof. The scientific community, quite reasonably, demanded evidence, and to prove that radium was a true element deserving a place in Mendeleev's periodic table, I needed to isolate it in pure form and determine its atomic weight with precision. This required years. Several tons of pitchblende residue and thousands of fractional crystallizations eventually yielded 1/10 of a gram of pure radium chloride, a quantity that would barely cover your fingernail. The atomic weight, I determined, came to 225, later refined to 226.45. Radium was real. It belonged in the periodic table, alongside barium, its chemical cousin, and it was not a compound of known elements, but something genuinely new. The examination committee at the Sorbonne, reviewing my doctoral thesis in June of 1903, declared it the greatest scientific contribution ever made in a doctoral dissertation. That same year brought the Nobel Prize in Physics, shared with Henri Becquerel, And radium was, by far, the most radioactive substance we had ever encountered. Let me tell you what radium does, and why it forced us to reconsider everything we thought we knew about matter. Radium glows, not like a firefly which generates light through chemical reactions, and not like the sun which burns through nuclear fusion at millions of degrees. Radium glows through a process that had no name, a process that nothing in nature had exhibited since the first seconds after the universe began. Pure radium compounds emit a faint, persistent, pale blue luminescence in the darkness of a laboratory, and they do this continuously, requiring no external energy, which we described as spontaneously luminous. What struck us even more was that radium generates heat. Pierre measured this with characteristic precision. A sample of radium maintains itself at a temperature measurably higher than its surroundings, and it does this constantly, hour after hour, day after day, year after year, with no apparent fuel source, no combustion, no chemical change. Where does this energy originate? This question haunted us, and it forced us to consider possibilities that seemed to contradict the fundamental laws of physics as they were understood. The principle of conservation of energy, the first law of thermodynamics, states that energy cannot be created or destroyed, only transformed from one form to another. Here was radium, sitting in its sealed container, emitting light and heat continuously, without any visible input. No fire heated it, no light struck it, and no chemical reaction consumed it in any observable way. It simply radiated endlessly, as if drawing from some inexhaustible internal reservoir. A paper I wrote in 1900 summarized this dilemma and captured two possibilities. Either we were witnessing a violation of energy conservation which would overturn the entire foundation of thermodynamics, or we were witnessing something unprecedented in the history of chemistry, the transmutation of elements. 5 years later, a young patent clerk named Albert Einstein would publish an equation, E equals mc squared, that revealed where the energy was hiding. Mass itself is frozen energy, and the atom contains energy equivalent to its mass multiplied by the speed of light squared. The energy radium emits comes from the atom, losing tiny amounts of its own mass, converting matter directly into energy. But that understanding came later. In 1900, we could only observe the phenomenon, and the explanation would require a revolution in physics that was still being born. Let me explain what transmutation means, and why suggesting it was nearly scientific heresy. Chemistry had established for over a century that elements are distinct, immutable substances. Gold is gold, lead is lead, uranium is uranium, and they do not transform into one another. This permanence of the elements stood as a cornerstone of modern chemistry. The ancient alchemists had dreamed of transmutation, of turning base metals into gold, but modern science had proven it a fantasy, and elements were supposed to be eternal and unchangeable. But consider what radioactivity implies. If the radiation emerges from within the atom, and we soon learned that alpha rays are particles with substantial mass carrying positive charge, then something must be leaving the atom. The atom is ejecting pieces of itself. If an atom loses part of itself, can it remain the same element? The theory that emerged, developed primarily by Ernest Rutherford and Frederick Soddy, and building directly upon our discoveries, proposed exactly this. Radioactive atoms spontaneously disintegrate. They emit particles, and in doing so, they transform into atoms of different elements entirely. Radium does not merely emit radiation, but becomes something else. A radium atom ejects an alpha particle and transforms into a gas we call the emanation, now known as radon. This radon is itself radioactive and transforms further through a cascade of successive disintegrations until finally reaching stability as ordinary, inactive lead. This was the transmutation the alchemists dreamed of, happening spontaneously throughout nature, everywhere, all the time, without human intervention. Radium becomes, radon becomes, polonium becomes lead. The atom is not the end of the story, but a chapter in an ongoing transformation. One of the most elegant confirmations came from helium. Radioactive minerals always contain trapped helium gas, always, without exception. If alpha particles are the nuclei of helium atoms, stripped of their electrons and ejected at tremendous speed, then the presence of helium in ancient radioactive rocks is explained. It accumulated over millions of years as uranium and radium atoms disintegrated one alpha particle at a time. What was once part of a radium atom becomes, irrevocably, a helium atom, a different element entirely. The atom, that supposedly fundamental and indivisible unit of matter, is not indivisible at all. It has internal structure, It contains parts, and some arrangements of those parts are unstable, destined to change. Consider what this means for your understanding of reality. The chair beneath you, the walls surrounding you, your own body, all are composed of atoms, and most of those atoms have persisted unchanged for billions of years. The carbon in your bones was forged in the heart of a dying star, and has remained carbon ever since, cycling through rock and atmosphere and living tissue without transforming. But not all atoms share this permanence. Within the earth beneath your feet, uranium atoms that condensed from stellar debris before our solar system formed are, at this very moment, disintegrating and ejecting particles and becoming thorium, then protactinium, then other elements in succession, working their way down through a chain of transformations toward eventual stability. The half-life of uranium-238 comes to 4.5 billion years, approximately the age of the Earth itself, but the process is inexorable. Half of all the uranium that existed when our planet formed has already decayed, and half of what remains will decay in the next 4-5 billion years. The energy released in these transformations staggers ordinary comprehension. A single gram of radium, over the course of its complete decay, releases energy equivalent to burning several hundred kilograms of coal. The continuous heat output that puzzled us in that cold shed represented only a tiny fraction of the energy locked within each atom, slowly leaking out over thousands of years. I have lived to see radioactivity transform from a laboratory curiosity into an entirely new science, a new kind of chemistry. We now work routinely with substances whose presence is revealed only by their radioactivity. Substances so minute that no balance can weigh them, yet which we can detect, dissolve, precipitate, and manipulate with precision. I have called this the chemistry of the imponderable, chemistry conducted not with scales and flasks, but with electrometers and radiation counters. The applications have exceeded anything we could have foreseen. The rays emitted by radium destroy disease cells more readily than healthy ones, offering treatment for cancers that were previously death sentences. During the Great War, I organized mobile radiological units, vehicles equipped with X-ray apparatus, so that surgeons near the front lines could locate bullets and shrapnel in wounded soldiers before operating. My daughter Irene, trained in these techniques, worked beside me in field hospitals, and she would go on to win her own Nobel Prize for discovering artificial radioactivity, the ability to make ordinary elements radioactive through bombardment. 5 Nobel Prizes have now been awarded to our family, and the work continues. But I must also tell you that these rays are dangerous. They penetrate flesh, they damage the delicate machinery of living cells, and they kill. The very property that makes radium useful against tumors makes it harmful to healthy tissue. We handled radioactive materials without protection, because we did not understand, in those early years, what we were exposing ourselves to. I carried test tubes of radioactive solutions in my pockets, and I watched radium glow in the darkness of the laboratory, marveling at its pale blue beauty without knowing that beauty was lethal. The knowledge of the atom's inner workings carries with it tremendous responsibility. The energy stored within atomic nuclei is vast beyond imagining, and humanity must approach this knowledge with wisdom and foresight. Science discovers, and it is for society to determine how discoveries are used. The same understanding that enables radiation therapy enables radiation weapons. I cannot control what others do with knowledge. I can only pursue truth and trust that truth, in the end, serves humanity. What I want you to understand is this. The discovery of radioactivity revealed that our most fundamental assumptions about matter were incomplete. We thought atoms were permanent, but they are not, because they transform on timescales ranging from fractions of a second to billions of years. We thought elements were immutable, but they transmute themselves spontaneously, one becoming another through processes we could observe but not initially explain. We thought the smallest building blocks of nature were simple and inert, but they contain within them forces and energies we are only beginning to comprehend, forces that power the stars and could power or destroy civilizations. When I began this work, I did not know where it would lead. I knew only that measurements disagreed with expectations, that minerals were too active, that energy appeared from nowhere apparent, and that substances changed their nature over time. These were facts, observations and facts. If you follow them with sufficient persistence and precision, eventually reveal their meaning. How limited is our direct perception of the world that surrounds us, and how numerous and varied may be the phenomena which we pass without the slightest suspicion of their existence, until the day when a fortunate observation reveals them. Science extends our perception beyond its natural boundaries and lets us see what eyes cannot see, measure what hands cannot feel, and understand transformations happening at scales of time and size that dwarf human experience. I have often been asked about the difficulties I faced as a woman in science, and these questions interest me less than the work itself. A scientist lives in a laboratory among measurements and evidence, and the uranium did not know or care whether the hands holding the electrometer belonged to a man or a woman. The measurements were equally valid either way. What sustained me through years of physical labor in that cold shed, through the tedium of endless crystallizations, through experiments that failed and had to be repeated, was the certainty that the work mattered. We were uncovering something real, something that existed before we looked for it and will continue to exist long after we are forgotten. The atom can destroy itself. This is not metaphor, but what actually happens. The particles fly out, the element transmutes, and radiation spreads in all directions. And in this destruction, something new is always born. A different element, a release of energy, and one more small piece of the secret architecture of matter, made visible to human understanding. We are surrounded by transformation. The very ground beneath your feet contains atoms in the slow process of becoming something else, atoms that have been changing since before life existed on this planet, and will continue changing long after our species is gone. This is not chaos, but order of a deeper kind, an order written in the fundamental laws that govern existence itself. Laws we are only beginning to read. The atom destroys itself, and in its destruction we discover what it truly is.